Hello, we are continuing our study of equiaccelerated motion, and today we will talk about how we can calculate additional parameters that we will naturally be interested in such motion. These are such quantities as displacement, path, body coordinate. To begin with, let's remember what the definition of acceleration is in general. That is, in the last lesson we introduced this concept. And today we can say that acceleration is a value that will determine the change in the velocity of the body per unit of time. We can conveniently create a graph showing the relationship between velocity and time using this definition. And for motion with constant acceleration, this graph will be a straight line. What information can we gather from this graph? First and foremost, in our previous lesson, we learned about average velocity. This concept allows us to exchange motion with variable velocity for motion with constant velocity. Essentially, we substitute the acceleration at a given point, which represents the change in velocity with a constant velocity in our equation. The average velocity is determined by calculating the arithmetic mean of two velocities. With these calculations, we can reach a deeper understanding of the graph's implications. The initial and final velocity. In this particular scenario, the idea of average speed is fairly straightforward. As we have previously discussed in prior lessons, average speed is usually defined as the total distance traveled divided by the corresponding time interval in which this distance was covered. It is important to note that even if there are different segments involved, including periods where the object remains still, all of these must be taken into consideration and separately accounted for. Thus, this inclusive approach allows us to accurately calculate the average velocity in cases where there is continuously changing velocity. By following this understanding, we ensure an accurate determination of an object's average velocity. What does the definition of average velocity give us? It allows us to determine now the coordinate of the body, because we will naturally be interested in where the body will be after a certain period of time. That is, its final coordinate. We remember the definition from constant velocity motion. This is what the equation appears to be, and in this scenario, of course, if we have made this substitution, we will replace the velocity, replacing it with the average velocity at which the body was moving. What comes next in this case? We already have knowledge of the definition of average velocity, that is, we can substitute it here, and the next step will be to solve the resulting formula. Thus, the final coordinate will now be defined in the following manner. The initial coordinate remains the same, and we will add the average velocity that we have already substituted into this definition. And multiply by dt, which is the time during which this change in velocity occurred. Well, we also know that we can find the final velocity of a body directly from the acceleration equation. Let's write it down again here. This is what this expression will look like, and we substitute the corresponding final velocity into our coordinate equation. The initial coordinate is constant, it doesn't change. And here we will now summarize the initial velocity with the terminal velocity. The terminal velocity has this expression. We're going to halve all of that and multiply by dt. Let's now summarize the initial velocity here. We can see that these are similar summands. We get the doubled initial velocity plus a dt and multiply all of this then by dt again. As a result, in the numerator we get the doubled initial velocity multiplied by dt plus a dt squared, and all this is divided by 2. Well, and accordingly here now it is convenient to represent this fraction as the sum of two fractions. To do this, we will perform an action called subtractive division. And let's write down here the already obtained expression for the final coordinate. So here we see that 2 and 2 will be reduced. All that's left is the product of initial velocity over time. So here we're left with just this fraction, which is a dt squared, divided by 2, So that's how you get the equation for motion. Can be classified into two main categories: equivariant motion and uniform motion. The key distinction between the two lies in the presence of acceleration. While equivariant motion involves acceleration, uniform motion does not. When analyzing uniform motion, the relationship between the coordinate and time is relatively simple, following a linear equation. On the other hand, equivariant motion exhibits a more complex dependence, represented by a quadratic equation that follows the shape of a parabola. To accurately depict this dependence on a graph, a minimum of 5 points need to be plotted, unlike in uniform motion where only 2 points are sufficient. As a result, the graph will display a distinct appearance, showcasing the dynamic change in coordinates over time. If the body initially has a coordinate and moves, we can represent its movement on a graph. As time progresses, the velocity of the body increases. Let's assume that the body starts from a specific point and begins to gain velocity. In this case, the parabolic shape of the graph indicates that the acceleration is greater than 0 and the body is moving with increasing velocity. On the other hand, if the body is moving with a certain velocity but starts to decelerate, the coordinate graph will have a different shape. i.e., the branches of the parabola are already inverted. When plotting the graph, we must take this fact into account and see how the branches of the parabola are oriented with respect to the time axis. Another useful equation for solving problems will result if we replace time, well, either in this formula, or, let's say, in this formula, we substitute the time just from the acceleration equation, that is, you and I in problems meet with a situation when the movement occurs with some acceleration, but we do not know the time during which the body moved. Therefore, in order to calculate the displacement of the body in such a motion, we will substitute time for the expression that we get from the velocity formula. So we get time from here is the difference between the final velocity and the initial velocity divided by the acceleration. Now this expression we'll put here. But here we, respectively, make a small substitution, that is, we move the initial coordinate to the left with a minus sign. Here we get the change of coordinate of the body, or directly the displacement of this body. Let's write it down immediately as the letter C, and then we're left with here the half sum of the initial and final velocity multiplied by time, which is the expression we're now substituting here. This is the difference of the final and initial velocity divided by the acceleration. What do we see in the numerator? In the numerator, we see the product of two expressions, and we see that in one case this expression has a minus sign. In the other case, it is a plus sign. According to the formula for reduced multiplication, we can now rewrite this fraction in its finished form. That is, the doubled acceleration appears at the bottom. Here we get then the difference of the squares of the given velocities. And we get in this way a time-free formula. That's how we can call it. Because in fact it allows us to determine the displacement of the body without knowing the time of this motion. That is, we simplify our task in solving such questions. From here we can also get the value of the final velocity. In order to achieve this, we will incorporate the corresponding equation into the square of the initial velocity. This expression can be commonly utilized in problem solving to determine the final velocity. Given the initial velocity, acceleration, and displacement of an object, we can apply it iteratively, provided we possess the required information. So, this is the end of our work. We will see you in practice. There we will apply these equations and see how to solve problems with the help of these formulas. Have a good day.